Welcome to Chapter 5 on circular motion and gravitation. In the last chapter, we began our study of dynamics, why things move. Now we continue studying dynamics, but now concentrate on the dynamics of circular motion. We'll be studying all sorts of neat applications like cars moving around, curves that are banked or not banked, or loop-to-loop problems, and also the motion of planets and satellites. So first, let's go over some key conceptual points. When an object is moving in a circle, we find that it is accelerating, even if the speed is constant as it moves around in a circle. Let's consider we have this ladybug moving around in a circle. And I can show sort of the path that it's following along in this perfect little circle. Now, why do you suppose the ladybug is accelerating? You see, here's the velocity of the ladybug. It's always constant in magnitude, but if you look at the velocity vector, it's continuously changing in direction. And so what we end up getting is an acceleration that is towards the center. In fact, if you look at them both, the angle between the acceleration vector and the velocity vector is perpendicular to one another. You see, acceleration is the rate of change of the velocity. And if the velocity is changing, then we have an acceleration. Now, an object that is moving in what we call uniform circular motion is an object that is moving at a constant speed. That's why we use the word uniform, but it's going in a circular path. When an object exhibits this kind of motion, then we always have an acceleration towards the center of the circle. This acceleration has different names. We usually call it the centripetal acceleration or the radial acceleration. It's a type of center-seeking acceleration. When an object moves in this perfect circular path at a constant speed, that net acceleration towards the center is always at an angle of 90 degrees to this velocity. And this velocity is sometimes called the tangential velocity because it's tangent to the curve. If you were, say, whirling a stone in a circle and suddenly the string were to break, then this stone would continue to move along its tangent line in a straight line due to inertia. Now, this center-seeking acceleration is typically called the centripetal acceleration, and it's usually denoted with a subscript with the acceleration symbol that we use, A. Now, to find the magnitude of the centripetal acceleration, it is given by the speed squared, or the velocity squared, divided by the radius of the circle. Sometimes you will also see the acceleration rewritten in terms of the period. So the period, which is capital T, is the time that it takes to make one revolution. Also, we have the radius of the circle right here. We can just write as r. So we know that if you were to look at an object moving in a complete circle, we could find the velocity by taking the distance that it travels around in the circle, which is 2 pi r, that's the circumference, divided by the time to make that one cycle, which would be the period. So this formula right here is not given on the AP formula sheet, but you should know it. It's really just distance divided by time, and the distance is the circumference of a circle. Now, also you'll see the frequency. Sometimes the frequency is given in problems. The frequency, which is this script F, is really just the number of revolutions that it makes per unit time. The typical units of frequency, the SI units of that, are in hertz. 1 hertz is equivalent to 1 revolution per second. The frequency is given as the inverse of the period. On the AP formula sheet, you get this formula right here, and you also get this formula as well. If you substitute t equals 1 over f into this equation, then you'll get another way of writing the speed in terms of the frequency and the radius. Now that you know that the velocity is calculated by taking the circumference divided by the time, 2 pi r over t, you could replace it into this equation for the velocity, and you'll get this equation for the acceleration now written in terms of the radius and the time. Okay, so we now know the kinematics of an object that moves in a circle will have an acceleration that is center seeking, which we call the centripetal acceleration, which is given by this formula over here. Now, if the object is accelerating radially inwards, then we can assume that there must be some unbalanced force acting on the object as it moves in a circle to cause this acceleration. The net force, or the net inward force, is really just given by Newton's second law. Sum of F equals ma, but we're looking at this special type of acceleration called the centripetal acceleration. So we substitute your a sub c with v squared over r, and you get this new sum of F for circular motion, uniform circular motion to be exact. So sum of F is equal to mv squared over r when you're dealing with things moving in uniform circular motion. Now, just a word about this. This is typically called in some textbooks not the net inward force. Now I find this is better just to call it a net inward force or just a net force. You will see in other books they call it the centripetal force. And over the years I find that's kind of confusing because people think that this is some new kind of force, like a physical force, like a friction or normal or gravity, but it isn't. It's just really the net force due to the other physical forces like gravity, tension, normal, and friction. So when we discuss the centripetal force, think of it as really just a net inward force. It's really just a combination of all these other physical forces. So for example, like this stone that is going around in a circle, what's the force that's really causing this stone to stay in this circular path? Well, it's attached to a string, and if it weren't for that string, then that ball would go off in a straight line. That string provides a force of tension acting on the ball or the stone. If the string were to break, there would be no tension and the ball would just continue moving in a straight line. So really, the net force in this case is really equal to the tension, and that tension is equivalent to mv squared over r. All right, the best way to learn this is to practice this with doing problems. So go on to example number 1 now.